Hi, we're ready to begin our second day of working with rational functions, graphs of rational functions. Yesterday we looked at vertical and horizontal asymptotes, and today we're going to look at our third type of asymptote, which is called a slant asymptote. You can see in the polynomial or rational function that I have here that there is a vertical asymptote at x equals 2. By the way, the scale on this graph is kind of funky. The x scale is going by 1, but the y is going by 5. So the x asymptote here is at x equals 2. However, you can see, or if you think about it, there is a slanted line in here, an oblique line, that this thing looks like it's butting up against, and that's exactly the case. Today we're going to take a look at that type of slant asymptote. So there's a vertical one at x equals 2, but we're going to be going to look for that oblique line of avoidance there. Slant asymptotes occur when the degree of the numerator is exactly 1 more than the degree of the denominator. So the degree of the numerator is exactly 1 more than the degree of the denominator. So there's our criteria. Remember, vertical asymptotes happen when denominators have 0 in them. Horizontal asymptotes happen when the degree of the numerator is equal to or less than the degree of the denominator. Slant asymptotes happen when the degree of the numerator is exactly 1 more than the degree of the denominator. To find the equation of a slant asymptote, you divide, folks. You follow what the thing says. Fraction bar means divide. So you divide numerator by denominator, and you disregard any remainder. The remainder is not important for this application, so you disregard the remainder. The equation of the slant asymptote will be what you get when you divide. So the equation of the slant asymptote will be the quotient. All right. The function on the previous screen had this rule, and if we were going to follow the advice here to divide, I hope that we'll be thinking about synthetic division, because that's fast and easy. So the coefficients are 2, -3, and 1. Divisor, well, you don't divide by the factor, you divide by the possible root that's associated with. So the root that goes with that factor would be 2. So we're going to drop down the first 2. We're going to multiply and add, then multiply again. And the last thing here is the denominator, which we really don't care about. But what we do care about is this. The depressed polynomial contains the coefficients of the equation of our slant asymptote, in this case 2x plus 1. And it wouldn't be correct unless we went ahead and showed that that's the truth. So I'm going to head for the calculator, and I am going to put my function in, need parentheses on the top, where 2x, okay, let's get that function rule in there. So we need the quantity 2x squared minus 3x plus 1 divided by the quantity x minus 2. Right, so here's our function, and let's set up a viewing window that shows what we had before. So we're going to menu and window and settings, X's are fine there, but the Y's we're going from, I don't remember, but I'm going to say negative 25 to 25. Let's see what kind of a picture we get there. Oh yeah, that's better. Okay, my claim is that the line that we found, which was 2x plus 1, I believe, I'll go back and look for that. Yeah, 2x plus 1 ought to fit, it ought to slide right in there. So I'm going to add a graph to what I had here, a function, and what I want to add is 2x plus 1. And sure enough, folks, that is that slant asymptote. Okay, we found that thing. We found that thing by dividing top by bottom, and the depressed polynomial is the equation of that slant asymptote, or that oblique line. I do want us to try it again. It says here that we're going to find the asymptote, so I guess we should probably check and make sure that we get an asymptote when x is 3. So I want to know just real quick, like, if 3 divides into this equally, because if it does, then we might have a factorable discontinuity. So I'm going to divide by 3, drop, multiply, add, multiply. Yeah, it's not a factor because we get a remainder of 20. So we should have a vertical asymptote at x equals 3, since it's not a root, and that would be somewhere, whoops, crooked line, right in there. The degree on top is exactly 1 more than the degree on the bottom. I've already done the dividing, so really I've already found the equation of my slant asymptote, which is kind of convenient. It happens at the line y equals, according to this, 3x plus 5. Actually, I'm going to just go right for my calculator and a new graph page. And let's see, grab that equation again. What we had was 3x squared minus 4x plus 5 divided by the quantity x minus 3. And according to what we did here, I say it should have a slant asymptote at y equals 3x plus 5. I am going to set a window that looks like the one that we have here, so I'm going to go ahead and press my menu key, and I want window settings, and x's are going in this picture from negative 20 to 20, so I'm going to make my window look like that, and then I'll sketch the graph when I'm finished here. Negative 20 to 20, and we'll let it auto size. Y's are going from negative 45 to 75. Y's from negative 45 to 75. And let's see what we, there it is. Good. So we got the function in there, and we can see that it is in 2 pieces, as rational functions have to be at least 2 pieces. What my claim is that the slant asymptote is the line 3x plus 5, so I'd like to see that at the same time. 3x plus 5. Hey, not bad. That fits right in there. So we got our slant asymptote. Alright, and the window that we have is similar to this one, so I am going to try and sketch that graph on the page over here. I don't know how successful I'll be, but I'm giving it a try. We got a branch that comes down here and slides along that way. We've got a branch that comes along here and slides that way, and the slant asymptote that we found hooks along through here. line of avoidance. Really, it is a sketch, and I know that's very sloppy, but what we're asking you to do is sketch what you see, and this was just a difficult window to graph that line in. So let's go on. This says that we should use what we know about families of functions, asymptotes, and tables to make graphs of these things. Let's see. We have a degree of 1 on top, 2 powers of x on the bottom. So this one will have a horizontal asymptote. None of these factors cancel, so I believe that we can say that we have a vertical asymptote, 2 of them at positive and negative 1. So very skinny in there. Positive and negative 1. The horizontal asymptote will be found by dividing by the highest power of x, and in this equation, actually we could multiply that bottom out and then that'll make more sense. X plus 2, and I look at this is first with a plus and then with a minus. This is x squared minus 1 on the bottom, and if you don't believe me, you can always run the FOIL or do the box method on those, and you'll see that that is x squared minus 1. The rule says that we should divide each term by the highest power of x in the denominator, so we're looking at x over x squared, 2 over x squared, but we already know that that's headed to 0. X squared over x squared, which is 1. And here it's 1 over x squared, which again is going to 0. So these are the important things. X over x squared, I'm going to draw my line this way. One x on the top knocks out 1 on the bottom, so that's 1 over x, and folks, that's going toward nothing, going towards 0. So our horizontal asymptote, if you collect all the stuff that you've done up there, is that y equals, it's 0 on top and 1 plus 0 on the bottom. So the horizontal asymptote is at y equals 0. So we have a line of avoidance right here. I'm not quite sure how things are going to play out here. So once I have the asymptotes in hand, I am going to head to my calculator. We are not expecting you to have X-ray vision with these functions. We kind of have to see what they look like. We can get an idea of where they exist by using these techniques, x plus 2. However, if we really want to know what the function looks like, it's probably best to go into the calculator. At least we have a framework for it. We're going to divide by, and then you have to open up a set of parentheses, and I'm going to type it in x squared minus 1, because that's the easier typing. And I'm going to go ahead and hit enter. And oh yeah, here's our graph. Now this one bothers me a little bit because we said that the horizontal asymptote was y equals 0. And I see that this crosses through the y equals line, but I'm going to remind you one more time. Asymptotal behavior says what's happening when x is extremely small. So when we get at super small x, this thing will approach 0 but not touch it. And you can see that on this side as well. We do have a little piece of that graph that's right in between those two lines. So this one's going to be kind of interesting to sketch, but I'll give it my best shot. We've got the volcano, kind of that look, and then this one drops, but then it's going back up towards 0. So I didn't know if I did a great job there or not. And then we've got a little piece in here that pops a little I don't know what you want to call it, peak in there that's popping up to the top. All right, good. Let's see if we can set up this one. And I think the first thing I want to check for, because I'm looking up here, a lot of 4s, and they are multiples of 2s. I'm thinking perhaps that factors. Really, we don't need the box for this, but we could use the x. 4 times 1, we need numbers that multiply to 4. At the same time, they have to add to 4. And folks, those are 2 and 2. So the top factors in this to x plus 2 times x plus 2. And guess what? We've got something that factors out of top and bottom. So there is a spot a problem spot, but not an asymptote for this one. It's going to have a hole or a point discontinuity when x is -2. Other than that, it's going to look like the line x plus 2, and that's the line that starts at 2 above and goes up in a slope of 1 over and 1 up and 1 over, so kind of going up in that fashion. When you get to x of -2 down here, function doesn't exist, but then it continues on that same trajectory. Had to factor on this one in order to see that oddity that happens. So that's the end of this lesson today, and I'll tell you, we've got some good tips for graphing these rationals. We learned about the asymptotes so that we know how to hang the framework of a graph around them. So you build kind of, I don't know what, I'm not an artist, but you build the background and then you hang the graph around it. So I often, in fact, I always want to know about the asymptotes first. Then I'll take a look at the calculator if I'm not sure how things go after that, and I hope you will do that as well. There is a U-try for this lesson that I'm going to encourage you to look at as quickly as you can, and we'll see you in class